3. So you could take 3 out, and you can make it 3 times this, right? 1 over n squared plus 4, like that. So you said you want to look at it as a p-series. It's almost a p-series, right? It's almost a p-series. Is that correct, everybody? It's almost a p-series. So you could say that that's less than 3 times n equals 0 to infinity of what? Why do we know it's less than that one? What did we do to get from here to here? We made the what? We made the denominator what? To get from here to here, we did not make it greater. We made the denominator what? We made the denominator smaller. By making the denominator smaller, what does that do to the whole thing? What does it make it? It makes the whole fraction what? Okay, everybody, let's think about this for a sec. If we make the denominator smaller, what does that do to the overall fraction? It makes the whole thing bigger. Makes the whole thing bigger. 3 over 2, 3 over 1. Which one is bigger? 3 over 1. You make the denominator smaller, makes the whole fraction bigger. What do you know this does right here? What does this do? We know that it what? Why, Chip? Since it is a p-series and p is greater than what? 1. In this case, p is equal to what? 2. So because it's less than something that converges, you know that it itself converges. So you could do it this way. There's another way you could do it. What's the other way you could do it that some of you might have tried to do? What's the other way? What? Integrate. You could try integrating. And while this is harder, one, it's possible and you need to know how to do it because you are going to be forced to use the integral test and you need to know how to integrate something like this. How do you do that? Well, what can you factor out first? Factor out the 3. Factor out the 3. Factor out the easy stuff that you can get out of there. So we're trying to integrate, 3 times the integral from 0 to infinity of this thing right here. What type of integral is that? What is it? It's an improper integral. So we should rewrite it first. This is 3 times the limit as n goes to infinity of 0. What letter do you want to use? Oh, I used n, but I was going to let you choose and then chose n. B to b of this right here. And we'll change, yeah, n, sure. It doesn't really matter. dn. Nice. Okay. Fantastic. How do we go about integrating that? You need to do, there's 2 important steps you have to get to. You have to do 2 things. What does that almost look like? It almost looks like what? We're not getting that good right there. 1 over what? What does it almost look like? This should remind you of something that you know the integration for. Tan. You know the integral of 1 over 1 plus x squared dx is equal to what? You have to know this. Nope, close. Tan inverse of x plus c, right? You know that. You have to know that. It's totally clutch. Is this almost that? It's really close to it, right? What's the thing that messes it up? The 4. So how do we turn that 4 into a 3, a 4 into a 1 legally? There's a couple things we could do. What's one of them? What? So you want to put the plus 3 there, right? But then how do you break apart that fraction? You see what I mean? Yeah, you could. I like that turn. That maneuver works sometimes. You could make it n squared plus 1 plus 3, and then just look at the n squared plus 1. But then how do you break apart the fraction, right? You can use u substitution here. What should I make u equal to? Anybody want to guess? And I'll make it something better than that. How about w? What do we want w equal to here? Something in terms of n. I'll just give it to you, n over 2. If I do that, what does dw equal? Differentiate for me, kids. This is not a trick question. What does dw equal? 1/2 dn. So what does dn equal? 2 dw. Substitute now. Now you substitute. If you substitute, a lot of this stays the same. B goes to infinity of 0 to what? B over what? Technically, B over what? It's now W, so it's going to be B over... What does... Look at this, everybody. What does n equal? 2w. So what does the upper limit become? 0 to To what? 2b. That doesn't really change anything because b is going to infinity, and if you're going to 2 times infinity, it doesn't change the character. But it's really important you do that because where do most people mess up when they mess up on U substitution? Limits of the limits. They don't change the limits. Okay, let's substitute the rest. What's it going to be over? 1 over what? You're substituting for n. What does n equal, everybody? So what do you plug in? So it's 2w squared, thank you, Chip, plus 4, and then instead of dn, what do I write? 2dw. You are now entirely in terms of w. We're in single variable calculus still. So can we simplify this? Say yes. Limit as b goes to infinity, 0 to 2b of 1 over, or not 1, what is it? 2 over 4w squared plus 4 dw. What can I factor out now? You can factor out 4 from the, and what can I factor out of the numerator? So it turns into 6 over 4. Oh, I got to put the limit in there. Don't drop the limit. The limit as b goes to infinity of 0 to 2b of what? 1 over what? W squared plus 1 dw. Is that something you can integrate now? Is that something you can integrate? What is this? So that's 3 over 2, limit as b goes to infinity of tan inverse of w from 0 to 2b. So that's going to be 3 over 2, the limit as b goes to infinity of tan inverse of 2b minus tan inverse of 0. What is tan inverse of 0? The question is, the tangent of what is 0? The tangent of what is 0? Close. It's 0. Pi over 4? Tangent is opposite over hypotenuse, so you need a fraction that goes to 0. So what angle are you at when the height of the triangle is 0? 0. So 0. What about this one, though? You have to remember what happens here. This is the key to everything, really, right here. Do you remember what happens to tan inverse as the angle goes to infinity? The way you remember this is, what does tan inverse look like? Do you remember what tan inverse looks like? Use your arm. What does it look like? Anybody remember? It's a that's tangent. Tangent does that. What does tan inverse do? It doesn't go up, everybody. Oh, it is. Yes, flip it around. From my perspective, you did it the proper way from your perspective. Absolutely. It looks like this. You know that tangent does this, right? It repeats. What does tan inverse look like? Like this, right? Do you remember what the horizontal asymptote is here? Y equals pi over 2. So what does this go to right here? Pi over 2. So this whole thing goes to 3/2 times what? Pi over 2. So did we actually find the limit of this thing? Yes. So if this all of that work was just to say, does this converge? Yeah, it did not diverge. It converged. So therefore, the series converges. Is this what the series converges to? No. This just tells us that the series converges because it has a maximum that keeps it under it that also converges. This is longer. Yes. Chip, is your way faster? Yes. Absolutely. But are there so many important things to this that you need to know how to do? What's one of them that you have to remember? What's one key thing you have to remember? It's in green up there in the upper right. You have to remember what the integral of 1 over 1 plus x squared is. Effectively, you have to remember what the derivative of inverse tan is. You need to remember what the derivative of all the inverse trig functions are. There are 6 of them. I see people recoil when I say that. That being said, it's totally fair of me to ask because I don't ask you to memorize too much. How much do you have to memorize in other classes? Way more, right? You have to memorize the derivatives of all the inverse trig functions because you're not going to prove them during the AP test. There's no credit, and what's your most valuable asset on the AP exam? Time.
Wait, which are the 6 trig functions?
All of the inverse trig functions. All of them. Know the derivatives of all of the inverse trig functions. Know them because then you get the integral of what their derivatives are. Everything is factorable, but is it factorable nicely? No. Now, Soma, you brought up actually how you can attack this. This is almost something that could be factored nicely, right? What is it really close to being factored? N plus 1 squared. So if you did n plus 1 squared, what does that equal? n squared plus 2n plus what? So what is this? N plus 1 squared what? Plus 1, right? What is that almost like? What is that? There it is again. There's tan inverse again, right? So could you use, so you're going to integrate what? From 0 to infinity of 1 over n plus 1 squared plus 1 dn. What can your u substitution be? Just a really straightforward u substitution. U could be what? N plus 1. So what's du equal to? Well, 1 dn. You need the dn in there. I'm sorry, my u's and my n's look the same. I'm just going to apologize about it, and I'll do my best. So can you do a substitution here? Yeah, you have the limit as b goes to infinity from 0 to b of 1 over what? Du. So what is that equal to? Limit as b goes to infinity of what? Tangent of... Oh, it's, by the way, it's b plus 1, and it goes not from 0, it goes from what? 1. That could be really important. That could be hugely important. Tan inverse of, what did I say there? U from 1 to b plus 1. So what limit are we actually doing here? We have the limit as b goes to infinity of tan inverse of b plus 1 minus tangent of what? Tan inverse of 1. It was important because what is tan inverse of 1, everybody? What's tan inverse of 1? Pi over 4. Yay, there it is. Hey, and what's, hey, what happens to this again? What happens to this? Boom. Or what does it approach? Oh, this approaches pi over 2. And this goes, this is just what? Pi over 4. So what's the answer to this? Pi over 2 minus pi over 4 is? Pi over 4. So does this converge? Yes. Hey, there it came out. So you get good at kind of massaging these equations to look like something you can actually work with. But the key to that is having it in your brain, the target you're trying to massage it towards. So for example, the other inverse trig functions, if you don't remember them, you're not going to know what to work towards on some of these. Could I easily change this to be like the secant inverse derivative? Inverse cosine? Will they do that to you on the AP exam? It's 6 things you have to memorize. Does anybody remember why these 6 are really annoying to memorize, though? Exactly. They're really, really similar. It would be so much more helpful, at least in my opinion, if they were wildly more complicated, but very different, right? They're really similar, right? One of them's like the square root of 1 plus. It's like, careful. You just have to flat out memorize them. Please do that. It'll help you.
So,
I think you had this one on the homework. It was talking about the harmonic series. Did you do this one? Yeah. It's pretty cool because it shows you one of the ways you can show it does not converge. What's the key reason? Well, it really comes down to this question right here, or show that, not question, but show that the sum of each group of fractions is more than 1/2. If you look at each group of fractions, you know that 1/3 is greater than 1/4. So therefore, you know that 1/3 plus 1/4 is greater than 1/2. Well, you know that all of these, those 3, are greater than 1/8. What's 4 times 1/8? 1/2. So therefore, all 4 of those is greater than 1/2 when you add them together. So with the harmonic series, does it ever end? So can you keep on making 1/2?
yes.
So therefore, does it converge? No. You can always add, you just guaranteed you can always add 1/2, which means you can always add as much as you want to it. So that's pretty freaking cool. That's pretty cool. I like that a lot. It's one of the ways. It's one of the ways. It's just important you know that because you'll use the harmonic series a lot. You'll use it a lot, yeah.
Are harmonic series like rare like that? Or are they not?
No, there are an infinite number of functions that do this. This is just the one that's like most straightforward to write. In math, there's generally 3 numbers of answers. There's either an infinite number of answers, 0 of them, or my favorite ones are the ones that have like 6 answers, or 4, or 5, some finite number. So generally speaking, if you can make one example, there's probably going to be an infinite number of them. That's anecdotal and kind of a joke, but kind of true. I love the ones that like you look at something in the natural world that seemingly is crazy weird, and then it turns out that's true. Like that's true. If you ask 100 mathematicians, 1,000 mathematicians, what's the sexiest thing in all of math? Like almost all of them are going to say that. Does anybody know what that is? What that's called? Yeah, what's it called? Yeah, Euler's formula. It's true. We will cover why this is true in a couple months. Using Taylor series. You can break this apart into this big long sum, into a series, and then guess what you plug into the series? You plug in pi I. What does I have a tendency to do? It keeps alternating and it cancels. So, like I to the first, what's I to the first? Well, that's I, right? What's I squared? Negative 1. What's I to the third? Negative I. And what's I to the fourth? 1. And then it cycles back, right? So when you plug I into things, they tend to cancel. Anyway, we'll look at this later, but it's really, really cool. And I love things that do this. Like, that's crazy cool, if you think about it. We have an infinite decimal that has no pattern, a different infinite decimal that has no pattern, an imaginary number, and that's negative 1. It works. So let's go back to reality. Let's go back to this. This right here is what we were talking about in terms of improper integrals. Improper integrals. This is one type of improper integral. Why is this an improper integral, Wiley?
Not because you're supposed to simplify it.
What element up here really makes it an improper? The infinity. You can't plug infinity into something because infinity is not a number. It's an idea. It's a concept. So you take it as a limit. Have we already done this a bunch of times already? We did this today, we did it yesterday, you're going to do it for homework tonight. It takes practice. Some of you have done it before, some of you haven't. It just takes practice. It's effectively plugging in infinity, but to make it mathematically correct, you must write it as the limit. I like B, the book likes B. You're free to choose whatever letter you like as long as you're consistent. How do we decide if this converges or not? Well, we just actually try doing this. We try doing this right now. Can someone lead me through it? Everybody else just watch, and who wants to lead me through this? Who wants to lead me through? Someone who hasn't spoken yet today. Who hasn't spoken yet today? Shirley, you want to tell me how to do this? How do I do this? What do I change it into first? How could you rewrite this to make it a little easier to see? It's x to the... Wait. So, what do you have now? 1 to b, yep. 2x to the 1 over 2. Oh, sorry, we're integrating now, so it's just 2x to the 1 over 2 from... Do we agree with this? What do we think? Is Shirley popular? Let's raise our hands. Is she popular today? Let's raise our hands. Yeah, she's popular today. Can we factor out that 2? I love taking the easy. You'll hear me say that a lot in this class. Take the easy. Yes, it takes about 30 seconds to, less than 30 seconds to write it over again, but do it. So what does this turn into? 2 times the limit as b goes to infinity of what? Minus 1, right? And what happens here? What does this do? What does this do? Boom! Goes to the dynamite. It gets real big. Gets real big. So what does this do? It diverges. So we just proved it diverges. We just proved it diverges because the limit, what happens to the square root function as x gets really big? Or in this case, we called it b. What happens? It gets infinitely big, right? You can always make it bigger, so it diverges. It diverges. Nice. Okay, get up to the board, everybody, with somebody who's not sitting next to you, and try this one for me. Try that one, diverge.
When p is greater than 1.
So it converges when p is greater than 1, and it diverges when what? Less than or equal to 1, right? The proof of that I'm not going to do, and you're not responsible for, but I highly recommend reading it. I put it in your notes. It's on page like 796 or something like that. You run an improper integral on it. You run an improper integral and you do an analysis. It's really easy to lose negative signs, so I don't like to write it out manually. You can read this. You're not responsible for it, but it's a great thing to read through on your own. It's a great thing to read through on your own. So I put it directly in your notes. But let's practice this a little more. We just did this one, though. Kind of. What's the only difference here? Can someone tell me what the only difference here is? What's the only difference?
Instead of being
1 to infinity, what is it? You're getting infinitely close to 0 on the left, right? So what did this graph look like? You know, 1 over the square root of x, what does it kind of look like? What's it kind of look? It kind of looks like this, right? I mean, it looks kind of like 1 over x. The curvature is a little different. So what did we find out before? When you went from, let's say this is x equals 1 right here. What did you know about this area right here? What happens to this? Does it converge or diverge? It diverges. What did we do just a minute ago? Look, it's hard to remember sometimes. But look, what did we do up here? Let's take a look. What did we do right? Oh, what happened here? Did we show that it diverges? What's it say in the bottom right? We just did that. It diverges when you go from 1 to infinity. So let's go back down here. What are we now checking? Not that red region. What region are we going to check? Like the left, we're talking about this region right here. So maybe we think that it's going to what? What if you had to guess right now, what do you think it's going to do? Diverge. You think it's going to diverge, right? Let's test it, though. You have to be very careful about it. Let's test it, though. Let's see what we do here. You do it the exact same way. So I like writing it like this. The limit as a goes to 0, a to 1 of x to the what power? 1/2 dx. So what's this going to be? The limit as a goes to 0 of, what's the integral? To what? To what? 2x to the 1/2 from a to 1. Where's the negative go? When you take the derivative of this, what happens to the power? You go down 1. 1/2 minus 1 is negative 1/2. Yep. So what do we have here? 2 times the limit as a goes to 0 of x to the 1/2 a to 1, right? So what's that going to be? 2 times the limit as a. 2 times the limit as a goes to 0 of what? The square root of a minus the square root of 1. What's that equal? What does that equal? Raise your hand when you got it. What does that equal? You can just tell me. Raise your any. What does that equal?
A minus 1 squared. A minus 1. Difference is a difference in 2. Oh, no, that's I don't know.
You're not factoring anything.
Yeah.
Just tell me what that limit is. Is it negative 2?
It's negative.
Oh, did I do this backwards, everybody? I did it backwards. It's the square root of 1 minus the square root of a. A is going to 0. So what does this limit go to? 2. Oh, look at that. Did we just find the area here? What is this area equal to? 2. Check that out, everybody. This diverges, but what does this do? Converges. So you remember you said, is it unique about the harmonic getting smaller and diverges? Well, no, this one diverges, but what does this one do? Converges, even though it kind of looks like it's really, really, really similar. That's pretty cool. I find that pretty cool. Thank you for noticing some of the small mistakes. So this is what we have before. This is what we were doing. Remember what I said, if you're below a convergence series, you are also converging. If you are above a divergent series, what happens? It diverges. That's what this says right here. That's what this says. That's what this says. It's just written out in the most compact way possible. So how could we use it right here? How could we use it right here? You could lead us through this, Chip. What could we compare this to? We know that this right here, we know that this, and you write out the whole thing, is less than what? Chip. Chip?
Is less than 1 over n cubed.
Yes, because we made the denominator smaller, so made it bigger. So, and you know that this right here diverges or converges. Converges, why?
Because that p is greater than 1.
Yeah, in this case, p is equal to 3. So if that converges, therefore what?
That converges.
This converges. And this is not all of the words I would like to see you write out. You would say, literally write sentence form if you wanted to. We've now shown that it is less than something that converges. We know it converges because it's a p series with p greater than 1. It takes 10 seconds, and it helps you clean things up. So either you're looking for something that is smaller than convergent or bigger than divergent. So you could take multiple steps. Like this one right here, what could we do first? So we know that this right here is going to be less than what? It's going to be less than what? What's one thing we could do to make it bigger? What's one thing? Delete the 3. So you could have n minus 1 over n cubed. And what could you do to make it even bigger, Shirley? Delete the... Yeah, you make the denominator bigger and you end up with this. But what does that equal right there?
1 over n squared.
1 over n squared, right? And what do we know this does? Converges. Therefore, that converges. But do you see how it's one direction? The entire time, what is it doing? It is getting bigger the entire time. So over here, you might try to make it bigger, but what's the problem here? If you delete a 1 from the top, if you make the numerator smaller, it makes the whole fraction smaller, right? So we want to turn this into something theoretically that diverges. And it has to always get smaller. If we go smaller than bigger, does that help us? No. That totally hits a wall for us. So if we do this, this is going to be less than the sum from 1 to infinity, let's say 6n squared over 2n cubed minus 1. And what's that going to be less than? 6n squared over. If you make the denominator bigger, it's going to make, 2n cubed. Does that simplify? Yes, because what did we do to go from here to here? The denominator got what? Sorry, the numerator got what? The numerator got numerator smaller. And what happened from here to here? Denominator what? Bigger. What? Oh, sorry. I'm writing the wrong symbol. It goes like this, right? Right, everybody? If we make the numerator smaller, it makes the whole thing smaller. If we make the denominator bigger, it makes the whole thing smaller. So smaller, smaller. Can we simplify that?
Yeah.
What's that simplify to? N equals 1 to infinity of what? 3 over n. And that's just 3 times, factor out the 3 times this. But what is that? What did I just write here? What is this? Harmonic. So it what? Diverges. Do you know what the 3 dots mean? Yes, you can use that. Okay, so remember, you either have to go bigger or you have to go what? Smaller. What happens if you go both of those things? It does not help you. You get nowhere. Be very careful about it. This is the last thing I want to show you because we're going to play around with it a little bit. This is truly the newest test here. This looks weird. This whole thing really comes down to this. If I put two series up against each other, and they tie, just go with me for a second. If I just take two series and I put them to battle against each other and they tie, either they are both convergent or they are both what? Divergent. What you're looking at here is you have two series defined by an and bn. If you run the limit of the sequence, so the terms, you're running the limit of the sequence, so the corresponding terms like a10 over b10, a11 over b11, if they converge to something, meaning they tie, if I throw a big thing up against a big thing, it might tie. If I throw a small thing up against a small thing, it might tie. If they tie, both of them have to be convergent or divergent. So for example, if you know that this one is convergent, but you're not sure about that one, but it comes out to say 7, what do you know about this one? It's also convergent. So this is not to test two series, it's to test one. Here's what I mean by this. This one right here looks like you might be able to use the same maneuver as before, right? Make it bigger, make it smaller. But the problem is, you want to get rid of that 6 and that 3. If you get rid of the 6, what does it do to the whole fraction? It makes it small. If you get rid of the 3, what does it make it? Bigger. Can't do it. You can't go up and then down. See? That n also makes it, you're nasty there. So what do you do instead? I'm going to call this an, okay? That whole thing. What does this do? Can you tell me what 1 over n squared does? What does that do? Does that converge or diverge? That converges. I'm going to call this bn. If I do that, I'm going to look at this limit right here. It looks nasty, but it simplifies real nice. The limit as n goes to infinity of an over bn. And in that case, what is it? It's the limit as n goes to infinity of n squared plus 6 over n to the 4th minus 2n plus 3, all over what? 1 over n squared. That looks terrible, but what happens when you simplify it? What happens? You end up with the limit as n goes to infinity of n squared plus 6 over n to the 4th minus 2n plus 3 times what? N squared. Over 1. So what does that mean? Limit as n goes to infinity of n to the 4th plus 6n squared all over n to the 4th minus 2n plus 3. Do you know the limit of that? What is the limit of that? It's 1. Why is it 1? Yeah, those are the only ones that matter, right? What's n to the 4th over n to the 4th? 1. So what did we just show? We just showed that the sequence of the fraction of these two things goes to 1. You know this converges, so therefore what must that do? It must converge. It must also converge. What about this one? you either want to find something that you know converges or definitely diverges. So you might be tempted to throw what at this? What might you be tempted to throw at that? You see sine and you think what? Yeah, so you think cosine of 1 over n. But the problem is, do you know anything about cosine of 1 over n? No. You know, though, this, though. What's this? What does that do?
Diverge.
That diverges, right? So what about this? The limit as n goes to infinity of sine of 1 over n over 1 over n? What does that simplify to? The limit as n goes to infinity of n sine over n. And this is a really cool thing because here's the deal. What is sine of 0?
1, 0.
Say it again with me. What's the sine of 0?
1.
There. 0. 0. It's 0. 0. So this is going to 0. But what is this doing? It's going to infinity. So you have this thing that's getting infinitely big, multiplied by something that's getting infinitely small, right? So what wins is the question. Here's the thing. You might have seen this before. You have to prove this. Sometimes you do this in AB. Does anybody know what this goes to? What does this go to? You eventually will use L'Hopital's rule to prove that, but I just want to know, does anybody know what that limit is? It's something you might have seen before. Wiley, do you know what it is?
Is this the one where it oscillates and dampens?
It dampens, but goes to something though. It actually goes to a number. Anybody know what it is? Yeah? What does it go to?
1.
It goes to 1, yeah. This thing goes to, this is really cool. Infinity and 0 go to war, and what comes out? 1. So here's the thing. We got a constant, but the thing on the bottom diverges, so therefore what does this must do? It also what? Diverges. This, the way you prove this is with L'Hopital's rule. We're not doing that quite yet. Hold on, Chip and then Steven. There's a couple ways. I know, there's a couple ways, but Chip, yeah.
Class